Considerations on planetary capacitance and its effects on EU geology. What we're going to be talking about is when you have plasmoids and balloons of fire coming down from the sky. What did these things look like to the people below? How much power is available in some of these comas and capacitance shells? And how much damage could one of these things really do? That's basically what we're going to be looking at. Given the recent instances of for example, Tunguska, but also Shoemaker-Levy 9 and the 2013 Russian meteor and its explosion. We should obviously be considering that there's more power than we think, given the apparent mass of these objects. What I'm presenting here is that there is an additional power. It is something that is measurable, and is something that we shouldn't think as fictional. We can calculate it. Now, give you an idea on how that works and how that would affect landscapes and the basic understanding of how our planet deals with things on that level. Literally what I've just said. So, an overview of planetary capacitance, the EU geology mechanisms, the principles on which they behave, pushing, pulling, or positive, negative, what that looks like to landscapes, and how this will help explain more EU geology mechanisms, recognize them when they're happening, or when they happened. So first, let's look at how planets work. The C unit, or is your idea of a Coulomb, is basically the charge symbol for its Q written in. I don't know why they chose Q, to be perfectly honest, but that Q is basically how much charge there is as a total number, sort of like how much something weighs. To give you a relationship, you can see on the next page, a 1 farad capacitor charged with 1 coulomb of electrical charge has a potential difference of 1 volt between the plates. It's very simple to understand. We use this all the time when determining how much energy a capacitor can hold, stuff like that. And of course, the distance between the plates themselves and the size of the plates determine how much you can hold. So let's look at the Earth. Just looking at the left side, you can see the general understanding of capacitors and capacitance, the relationship between them. And you can see that the Earth does have about 500,000 volts. This is not always the case. We can be a little bit lower, 350,000, a little bit higher, 650,000, but somewhere in that general area. So 500,000 is a good mathematical number for this. And of course, when you're looking at this, what this is going to mean for the circuit itself, how do these come into play? What is a fair weather current? Because if you have a fair weather voltage, you must have a leak across the dielectric, and it's a fair weather, of course, current. So how does this circuit generally work? I'm not going to go into incredible detail because we're going to be talking about static charges for the most part, but these charges are actually moving, and they obviously then therefore have electromagnetism involved. They store energy in their magnetic fields. This energy, of course, is induced and can induce into other magnetic fields. As you can see here, if the energy is pouring into here, this is where you get the auroras. But at the same time, this is where energy is stored along these rings here, the Van Allen belts. And that's generally how you would have a energy flow, if it were. And it spins them up here. It's described very clearly here. You have current going in. It's going out along here. There is an induction going around in an opposite direction. And you can envision the same thing happening underneath the surface of the Earth as well. Capacitors resist changes in voltage. That's their thing. That's how they work. We use them to hold up a voltage. They can stabilize against certain frequencies. They make DC passage very difficult. You have to basically completely cause a breakdown to get through it. So the Earth itself, it has an ionospheric shield, as it were, and it has the ability to take this energy that is directed towards it, perhaps in the form of plasma blobs or impeding bodies, and it can utilize this energy to destroy incoming bodies or to store the energy of for example, a CME that would hit us. We've learned from Michael Claridge's work that the Earth will kick up the voltage and form additional rings to store this energy, sort of, or maybe not unlike shells on an atom. Here are the two basic ideas that we're going to use and the formulas that are going with them. So the force on any given particle, that's basically the math to describe it. Ke is just a constant. Q1 and Q2, that's the total charge force between the two coulombs, and the distance between them squared. So it's the R-square law. It's identical to the gravitational formula, except G, which would take the place of K, and M's would take the place of the Q's. Otherwise, it's the same. Now, of course, the force on any given particle with regards to mass, the gravitational constant is incredibly weak. However, the force on any given particle with electricity is 9 billion. That's newtons. So, yeah, it's just incredible comparatively. So you can basically then understand the power and the distance between the plates can be solved for, as you can do it here on the right-hand side. Basically, you can rearrange the formula and you end up with the plate distance being equal to the area times the voltage over the charge. We rearrange it because this is what we're going to be using a lot to try to figure out what's going to be happening to the ionosphere here when something starts coming into it, or perhaps a massive blob would come towards it. Now, again, I'm using static electricity. This is just basically applications of an understanding. Given that this is actually filled with moving charged particles, this is not entirely accurate at a given point, because they will create funnels, and of course we see all the wonderful things that happens with weather on the planet. So don't think of this as the be-all end-all, but it should give you a good understanding of what's going on. So we're going to solve for distance here. During the 2004 tsunami, this magnitude of earthquake, 9.3, the ionosphere dipped in 30 to 40 kilometers. So the ionosphere, being around 50 kilometers up, suddenly drops into 20 or 10 kilometers, which is well inside the atmosphere. Was it something from the outside that was causing this to be forced down, or was it something in the ground that was causing it to be drawn down? There is no way of really knowing unless we have something visual, but it is an if-then statement, because if the ionosphere is drawn in and we solve for distance, we understand then that the parameters have changed on our equation. The Q must have changed since the constants haven't. So let's look at how the shield might interact with a low-charge bolide or meteor coming in. So it's the bolide, being positively charged, is going to push against this positively charged ionosphere, causing it to go down, dip in. This is, of course, changing the plate distance, affecting the ground beneath it. If it is pulsing or otherwise causing breakdowns at the time, then piezoelectric effects in the ground could resonate, and you could get sound, even though this thing is in space. Still, technically, the rocks around you would vibrate when this thing came down, which was discussed by witnesses of the Tunguska bolide. When it came in, people could hear it well before the shock wave, which was supersonic, hit them. So that was impossible. What they must have been hearing then was the resonance of the piezoelectric rocks around them that were resonating to the flaming fire above in the coma of the incoming bolide. This is a small one, low charge, But you can see what would happen. As soon as it gets further into the atmosphere, it's going to be surrounded by negative charge, and it's going to have a coma around it, not unlike a space shuttle or the Saturn rockets when we saw them come in there with their parachutes and such. So low charge, nothing's been up there for very long, something we can easily deal with. But that's not always the case. So with a moderate charge bolide, this is what starts happening. The force of the positive charges are pushing down the ionosphere much more. Then it pierces it. It can't pierce the ground. The ground's a solid plate for this, all intents and purposes, a solid negative plate. The ionosphere is a movable positive plate. So as this pierces it, it goes further and further in, and it will start affecting the ground. Now, this is what I was talking about with the piezoelectrics. It builds up charge between the ground and it, as well as building the coma around itself. The negative charges of the Earth sense that bolide so much positive charge there that it is attracted to the ground underneath of it. It starts feeding up leader charges and so forth. And of course, this is when amazing explosions and fireballs would probably occur. So let's talk about that. So the general energy, or in joules of fireball, that's the formula for it. You can understand simply then that the capacitance, which we talked about earlier, and the voltage, which we understand what that is, 500,000. Let's just put that understand it mentally. And of course, just divide it by 2. So the amount of energy that you have there is significant. When it was talked about those people that were killed and people that have been vaporized by these things, it only takes 120 to 180,000 joules to cremate a body fully to dust. So we're talking, let's just put a number here of 10 on the C. Let's look at 500,000 for the V. And then, so how much energy is in that fireball? Exactly. You don't even want to imagine it. So that's why when they come in, they say, "Oh, it's a very small fireball. But it must have been very dense." Why is that, Jim? Well, we did the math, and the math says that the energy, because we have these sound recorders around the world that can tell the sonic pressure wave. That's how much power it has. It had to dissipate that power in the form of shock waves, including light and so forth. So how much power was it? Well, it tells us that this weighed 10,000 tons. But I thought you said it was only 10 tons. I know, but it weighed 10,000. It had to, because math. Well, I'm telling you, you're only using half the equation. If you're using physical forces with regards to Newton's laws, you're ignoring half of what we've ever learned about how these things work. And you can understand completely why combining some of these formulas together involves breaking down. When the meteorite over Russia exploded, you saw the arcing of the light as it came down in the morning, and the whole surface was on fire, trying to find a way to break down this capacitor. When it finally did, it tried to increase its surface area. Now, when you increase your surface area, this is what Don Scott calls electrical fissioning. Basically, the capacitor breaks down, and when it does so violently. Everything bridges across that gap, just like it does in a nuclear fusion reactor, which it sticks to the side. Well, this is the same thing, but this is made of rock. So when it breaks down, it does so violently and increased its surface area by exploding into a bunch of smaller balls. And it became a shotgun of debris. And, well, we heard the explosion. Not unlike when we hear the explosion of a volcano going off. It sounds like it's just a bang. It's a boom. It's not a popping conflagration or anything like that. They're incredibly devastating. So let's apply these principles then to geology and see if we can narrow down some understanding of what we have here. In our toolbox, we're going to be looking at excavation, Lichtenberg excavation, V-shaped trenches, electric creating blue holes. These are the excavation types. Each stage, 1, 2, and 3, would be a degree of power or a scale. 1 would be a very powerful version, 3 would be the weakest. One of the other things, though, is the mechanical effects, especially with regards to glaciers and so forth. I'm going to be going over those and showing where we might be making a grave mistake. So with excavation, you can see clearly that just by looking at this wonderful example here, this is on Baffin Island, that 2 rivers are crossing themselves. You can almost see 3 as up at the top to this part over here. You can see where there is a etching that went through, crossing this path, and tried to continue up. Well, it did continue up this way, but without as much power. This is the cross-hatching action that we've talked about many times on the show. Electricity tends to do this when it's scouring an area. You can envision 2 twisting fire tornadoes going across the landscape, horrifyingly quickly, ripping land up. That's basically what we have. Whatever land was up here, I mean, I'm sure it was nice, but it's gone now, and the only thing left is the rocks. And ice is just filling in the cracks. There's no possible way that moving ice can make an X. Rivers don't do that, ice or otherwise. I'm sure that we can all agree on that, at least. That's a falsification image. I hope you've been taking a look at the information to the left here. V-shaped trenches are the signature that you're going to see. You can see them in the background there. Very high steep. They come down, and then they go in and down and in and down and so forth. And I'll give you some examples of those. Here is this exact motif in 2 separate places in the world. We can see Egypt on one side, Yemen on the other. Now, you can see the etching that I was talking about from a higher perspective. This again is Baffin Island down here. And this image, you can see just cross-hatching all over the place. Perfect examples down at the ends. And Donald Scott talked about that when he was talking about the etchings on Mars, where parts of it would just keep on crisscrossing the same area and whittle down the material into smaller and smaller versions of itself until finally there's only a few spires, like in Monument Valley. Places where rivers were, you can get this crisscrossing like you see here. And you can see this still a very linear direction to the work, even though it is going around the river. This is perfect examples of what we're talking about. This is the Grand Canyon here. And this is the V-shaped trench. You can see lots of these. They're called glacial trenches, actually, in northern Canada. And I assume northern Siberia as well. They basically function exactly in the same principles. You have a negative surface. Positive charges remove the surface. It does so depending on the force it can impact the surface with. In this case, of course, voltage will give you depth and current will give you width. So in this particular scale, you can see that there's a whole area that got scoured, and you can see in the distance where the surface matches up. It's like this and this connect, and then there's a deeper part over here. But these flat surfaces are parts like this, except they've been eaten away completely. And of course, you can see that in Monument Valley as well. And all over. That's, of course, the Grand Canyon from above. You can see the deep Lichtenberg figure. Even beyond this picture, out into the distance, there's still that V-shaped trench, much like you can see here. And this is what it's founded on, the electrical principle, just exactly as it is described. So you have a voltage source, a cathode, and anode. Now, these electron pathways, notice they are in pairs. This is a characteristic of plasma, and as soon as it begins to ionize, you're going to get these loops. This is exactly what Andy was discussing when he was referring to looping idea of prominences and so forth. And you can also see the exact situation with, if you've ever seen any arches, that's a characteristic, an induced characteristic, but something that you can see in physical form. This is basically how it functions and why it looks like a V shape. Notice the ionization pathway is very deep in the origin. That's why the voltage determines depth. The voltage breakdown point will be deeper depending on the voltage. And then, of course, it will go upwards. You can imagine then, because this deep, deep middle trench of the Grand Canyon would be that point there. And everything else is a characteristic of that. It's called a Thompson avalanche. Now, when you're not getting a complete circuit anymore, things begin to break down, you're going to see these loops. In the negative, these loops look like these spires. You can see where they can't quite etch everything completely. You can see the cross-hatching. Again, here it is. So we know that there's current running this way, and then here's a cross-hatching of it like that. And you can see it in many different places here. This is the scalloping you might see on, for example, Valles Marineris on Mars. Nice scalloped edges. Lichtenberg figures everywhere. But you can see this is eaten away, just totally, but not to the same length. This is basically along the end of the Grand Canyon. This is called Bryce Canyon. You can see incomplete electrical excavations of craters as well. Now, if you look at the base of this is Victoria Crater on Mars here. And you can see these little points. If you imagine every single little base of those as a crater, those were the beginnings of a Thompson avalanche. And that's what ate this whole thing out. Probably did it very, very quickly. It came down as a beard of fire, as opposed to twisting. The large circuit filaments that we see in Jacob Gabel's work with the 2 or 6 streamers, those type of things where we see hexagon craters or just regular craters like these. Now you can now get an idea why you see 3 in a row that look perfect like that. It is this principle of these would be the base of 3 Thompson avalanches just in a row, but you can see there was a lot going on here, and they were very small and very fine. If you want to see a V-shaped trench in a disk form, there it is, bullseye craters. Perfect examples. It's the same idea as a V-shaped trench, except as we know now from Jacob Gabel's work, and I love referencing him, by the way, this would come down and it's not nearly as, it doesn't have to create the avalanche effect nearly as much, only on the surface, because the air itself does not have to break down, because there's not really any air to break down, if you get my meaning. This effect dances around, and you can see where it reaches down to the deepest point where it can find a place to sit, and it will eat out the area around it as it does so to a larger and larger level. And you can see it was continuing scalloping and layering and so forth. This is another point where it was probably jumping to, and there's another point that it was probably jumping to. And it was probably doing this, all of these points at the same time for a bit, as we have seen in experiments. As much as we would like to think of them as impacts, and when I say a bit, I mean no more than a few minutes, maybe a few seconds, that type of thing. So, let's not think that they were. Now, it could have been going on for a little bit longer, but chances are the impactor would be destroyed if it was big enough, or shoved away and moved along if it was a planet. So this is why I say that it's premature to think of it that way. But sometimes we'll see incomplete, which is where we see these two hits together, just two footprints really quick, boom. And they blast out material in both directions, but don't actually eat that middle line down. Sometimes they are caused by perhaps maybe a body is moving across the surface, or there's something under the surface that causes the material to bubble up and break, as we've seen with aquifers, or the potential of that. And so as such, the material would be vaporized underneath, and the crater would be malformed. Up close, you can start seeing what we're talking about. This is the edges of meteor crater. This is the actual ground here, and this is the rim lip. This layer here is reverse of this layer here. And the only way to explain that correctly is, of course, as something was moved from here to here, but it was not chaotically blasted as in distance this way, linearly. It's this way, which means that this material was etched layer by layer by layer by layer by layer by layer by layer, and so on, using the laws that we described earlier, the force on any particle. In context, this is right there at meteor crater. This is the same scalloping we saw as it was etching, electricity was etching the landscape around it, but this is a much smaller form. And you can see that these Lichtenberg figures are right on the rocks, clear for anyone to see, right there beside the steps. You have to be pretty blind not to see these falsifications. Here's a falsification. How the heck did that happen? That's impossible. That's impossible. If this is a river of what? How did it go up and down over landscape? Why that's not talked about is beyond me. I have no idea. It's almost like you have to take effort to not see it. Same thing here. This is your cross-hatching effect of electricity again. So here is a direction. Now keep in mind that we're going to be seeing a lot of this as I go on. Here's the main direction. Here is induced direction. And these are craters from whatever body was passing along the surface, jumping from point to point to point to point to point as it went along. But it was also etching a secondary channel. It's like it had two layers. This is the middle channel going down, just like you would see in the Grand Canyon, but unfortunately there's no atmosphere. And since there's no atmosphere, it doesn't behave like it does with Lichtenberg patterns on the Earth. It doesn't have to do that dielectric breakdown. So it can move across the surface as it does. Victoria Crater, as I was saying, this is the bearded effect that I was referring to that will likely have created it. The points are breakdown points down near the base. The Thompson discharge down here would be these points down here. This is why we can get half craters, half canyons. This is the crater, obviously, in the edge of the Badlands. You can see the landscape was continually etched for a period of time, but a crater did hit. This means a electric touchdown was here, but it continued etching anyway. So this could have been made like, and then it will continue etching and etching and etching and etching, and eventually that crater would disappear if it continued. It didn't, and we got the chance to see a half-made one. This is not unlike this here, the rim crater on Victoria Crater on Mars. This is a similar effect is what we're seeing. This is just a larger strike. This is just a larger strike to a higher point. But the bearded effect was likely in play, if you can envision it. This is a new area of exploration. Blue holes. We know they exist. They don't seem to behave the way that we'd think geologically they should. As you can see from just this image, there is a hardened shell at the top here. You have rings around it that appears to be where this might have been etching downwards, and it found a place that was good to go for. It's saying, I like the electrons at the bottom of this thing. Whatever's down here is giving me what I need. And it could be water, it could be hematite. We've seen examples of both. As such, it will reach down, and once it's at a lower power level than a full arc form. It's more like a glow mode, and as such, it is twisting like those pillars of fire that we've described before, a tornado of fire, and it would burrow down through the ground. It would melt as it went, well, actually more like tear off as it went, and we can see that there's not enough material at the bottom to describe how much was actually etched out. Most of it would be lifted up and away. And it found material down here that it liked, and you can see the edge would be continually melted because it's looking for more surface area. A rock of higher conductivity allows this effect to be more pronounced because this is insulative rock. This material down here was able to give it the electrons that it wanted in the volume that it wanted. It's not necessarily proper to think of electricity as having goals and desires, but if it can get more easier, it will. It's like water flowing downhill. It is a truism. You can envision then, I hopefully see how that would function and how it would be likely a sustained discharge. Now, they don't just occur on Earth. We can see some examples here on Mars, and we can see a perfect example of the exact same thing I think this is New Mexico. There's no water, so it certainly wasn't erosion of the aquifer that they might describe here. I attest that perhaps there was something similar in both instances. You might notice here this ripped out edge. We've seen this in David's work, Electric Universe Eyes, where he was ripping chunks off, and you can see how it was ripped off and instantly vaporized. Well, this is an example of something that might have done that. Just, it's gone. If you'd also note, if you can see this here, this is not terrain. So here is something, a shadow going this way and probably around like so, and from here up and around like so. You can see also the faint happening here as well. I'm guessing at that one. I'm not sure if it's even there, but that looks clear to me. So this would be the debris that was removed and turned to dust and spread along this area. Now, because it's Mars, this would likely be, just like it is on Earth, a silicate, something difficult to chew through, but with sustained arc burning in the same area. These were probably doing this at the same time, by the way, just perhaps back and forth as two tornadoes twisting, bouncing here and there perhaps. But as such here, this might be hematite, for example. We do know that there are layers of that on Mars, and if it found a layer of that to reach for, that would be very good. It's highly conductive and allows more than enough electrons to come through. Now, some of it be, of course, ripped right off the surface of the hematite down in the bottom of this thing. And this is probably that darker debris here. The whiter debris would be underneath of it. Interestingly, I do know at the bottom of the one in New Mexico, it stops at a layer of hematite. Here's some examples on, I believe this one is on Mars and that one is on the Moon. You can see here now the problem with them. They're not worn by water. There's no smooth sides. Nothing here. There's not enough debris at the bottom to indicate why it looks like it does. And note how it looks like just like it did in the former picture. Has a perfect example of what almost like a crater. But it was burrowed through. And it would be the same thing on top, just a pillar of fire, ripping out anything nearby and taking it up that chute as it tried to get at the electrons down here. It just needs charge carriers, and vaporized rock would be just perfect. We can see that there are caves sometimes reaching off the sides of these things. Again, this is underwater, I believe, so I'm not quite sure. If they try to infer, basically, this is where the sea level was and so on. They're trying to say that maybe this was carved by water coming in and out, But I don't think so. I think this is probably just like the Grand Canyon has arches and canyons reaching off the side. Most of these objects do, especially when you get the V-shaped trenches. Well, in a similar fashion, and much like a crater, perfect example, it's ripping material out, throwing it to the sides, and now this material is still here, giving it current. It's etching down. It gets down to the bottom, whatever it is, perhaps maybe water, who knows. This here is now going in, and it goes, well, I want more current. This is still a perfect pathway, but it can go this way now and then down over here to find another connection to this pathway. And it will, and it did. That's what I'm attesting. So these things are not behaving like some people think they are. And this is why we have such interesting crystals and beautiful structures inside these caves, untouched by water. Water had nothing to do with it. And I'm not saying that's every single one, by the way. I'm sure that there are. I mean, I've seen water caves. I live on the Bay of Fundy, but they don't look as cool as that, I'll tell you. This is a spill of burning sulfur, if you want to get a vision of what pillars of fire might have looked like. These would have been witnessed by, they would be burning a hole in the ground, and this is the principle which they would be behaving under. Using the same basic math that we were talking about, they would build a charged teeth vortex, not unlike a tornado. You would have a spinning vortex of charged particles. One would be spinning one way on the inside. On the outside would be another. This is where you get your shells. Sometimes I was talking about, for example, the one where you saw the crater chain inside a crater line or trench. Well, that is an example of this going across the surface. You would have a debris field down here, but because this is an airless body, or most of these were, the debris field would be much more diffuse and much more subjected to electromagnetism on the particles. Unfortunately, the air of the Earth has a dampening effect. As you know, tornado debris fields are just down near the base, and they throw material up and out like so. But there is a charge coming up from the ground, this negative charge, that is attached to the Earth. And, of course, you have the same thing here coming down from the upper cloud layer in a tornado, spinning in the opposite direction. Now, to take that to the extreme, this would be what would be happening if a tornado could be so powerful that it would stay on one spot, be on fire, and continue burning into the ground. So our ancestors would have witnessed stuff like this. This is where, when I said that there is more going on than just electrostatics, this is what I meant. This could have been induced. This could be an effect of a dipping down of the ionosphere in a particular location. It could be caused by incoming bolides. It's unfortunately not easy to predict what would be causing it, but anything like that could create what would be effectively, it would just be the worst storm you could ever possibly imagine, like a supercell storm that was larger, like the state of Utah, spinning on fire. Perhaps Andy Hall talked about something like this in his recent Space News. And it would be spawning these tornadoes of fire. And these tornadoes of fire would be in the dozens in any given direction or more. And some of them would stop as they found a good spot to burn through. Like, say, they found a water table with lots of charge down there, lots of negative charge it wants to get to. Now, this ground is giving as many electrons as it can, but it's not giving enough. The storm wants more, but the atmosphere's thick. It can only come down in certain points. It's trying to reach through with these fire tornadoes. As it does so, eventually it sees a point like this aquifer. It starts going through the rock, ripping rock up using the equations that I mentioned before, the forces mentioned before, coming down through, burning through this particular material. Once it gets to these electrons, it will use this conductive pathway to extract those electrons. And that's what it's doing. Now, deposition is pretty much the opposite of that. if you were having positive and negative points on the Earth, this is where the other side of the loop would be. Prominences and so forth. Sometimes they can happen just beside each other. Sometimes they happen in areas where you can see clearly that this was just laid down, just pure deposition. So we're going to go through some of the scales of this to give some understanding. Mountains being the largest that we have, we're talking about heavy basalt, iron-rich material usually, layering down over top of entire areas. Some of this would be considered tough. It would be layering in a windward, leeward direction. They seem to have so much material that whatever was there before is completely and totally buried. Obviously, we do know some of this is volcanic in nature and so forth, and we're not denying that. But some impossible to ignore that it has almost magical property to it. So here is an example of that layering. There's some people there for scale. Here's this wonderful ridge of rock. You can almost see how it was laid down. It's affected by the magnetic fields as it is laid down. It comes down in giant towers, pouring in and welding to itself as it does so. Not unlike spray painting a bicycle when you were a child by applying a voltage to it, and you could paint both sides at once because the paint would stick to it. You can see that sometimes it appears that it's hard to tell the difference. Here's something that looks like it might be electrically etched. Probably did have some etching, but you can see down here at the bottom these particular pieces of material. Likely it was deposited and built up. And here are some much more clear examples of tufting going instead in the area. You have one of the characteristics of deposition is a windward and leeward side. This material is usually completely incandescent. It's subject to the atmosphere, the winds, shock waves. This is why we see examples of breaks in the rock as it's laid down. Robert and I have explored this at great lengths, as you can probably see in our EU Geology Tour video that we had there. So, but here's some other examples of preferential layering. It doesn't have to be layered perfectly like it is here. Like here it is layer and then red, black, and these are all different materials, by the way. Some smattering of different materials here and so on. But they could also be sorted like so. This material is dumped over here. This material is dumped here. This material here, and this material here. So this would be like wind blowing down, raining down, and welding and building up in this direction. So it's coming in, blowing across the landscape, building up and building up and building up as it does so into the wind. And this is what this constitutes. This here, more like a prominence. Excavation was happening all over the area. You saw how material is lifted into the sky, but then it is twisting and sorted electrically and then dropped back down. And this is what we're seeing here in different locations. Now, this is affected by water much more than mountains. Mountains could probably just have so much material it could cover up a lake, if you know what I mean. Like that's probably why we have underground lakes in the first place underneath a mountain, because even though the material was falling into the water, it became sand as soon as it touches the water, and but the mountain built up around it because it has magnetic properties as well. So it can make a roof over top of this thing and completely make a cavern and not affect the water. Like the water still stays there. Because remember, it's not asking electrons from this water. It was asking electrons from that water. It's giving electrons to this water, which the water doesn't give a crap about. So it already has enough. It's thanks. And so it just welds to the surface. And as it has higher basalt and other types of material to it, there you go. You can start grading an arch much better. This material here, for example, coming in, not so much. This material is layered down. The water is able to stop it. The material, the water could be a bit higher, you can envision, maybe to the base here. But either way, the material comes in and is unable to stick to the water at all. As such, the water just carries it away, so it builds up around it. This seems to indicate then that some instances water was present, and we can see that because the water has seemed to shape the landscape. Material on one side is completely different than material on the other side. There's no reason for that to have occurred just because water is there, unless water was the reason why that happened. When we go a bit further up north, we start running into these things. Eskers and drumlins and so forth. They're considered glacial patterns. In the background image, you can see some of that as well. Striations, not unlike we have seen before. However, this stuff is in alluvial form. It's not welded together. It seems to have deposited after it had cooled, not unlike volcanic ash, perhaps. So this should give you a concept. And of course, northern Canada, Siberia, places like that are totally inundated with it. We see then that the poles of the planet seem to have these wonderful mountains and so forth with ridges and ranges, but deposition clearly continued occurring even if the mountains were already established. Now, these things are supposed to be formed in particular ways, geologically speaking, inside of the tunnels of glaciers and so forth. However, the reason they're said that is because they're supposed to go through tubes because they do not obey up and down as water should. So they were thinking that it must be pushed up by a tube that being held down by the ice. And this is what causes this. Now, of course, we see these form positive Lichtenberg figures. They just clearly do. And let's go a little bit further into that, especially since we see these on other planets, which, if they are made by glaciers, they have no reason being there. These are supposed to be, as I said, glacial deposits. You can see here, these are drumlins. And they are mounds of earth, more or less. Mountains of earth, you could say, but they're not obviously very big. So this is why I put them as like the number 3 of the deposition world. This is supposed to be the remains of a glacier that was here before. We have these straight lines. That's a crater, or is that a lake? I don't know. But you can see that there is a possibility that could be either. So let's go a little bit deeper. Some of these are on Mars, some of these are on Earth. As you can see, these are esker-like ridges. These are supposed to apparently be there, but because of glaciers coming off of this crater rim, apparently. But that makes no sense in our world. In electrical terms, these are just streamers coming off of a hit, and positive streamers going across the landscape, not unlike ship rock, pulling material into tubes through that through the filamentary effect of plasma. And this is what they're doing as they pull material along towards these strikes. You can see this one is in Ontario, if I'm not mistaken, or Michigan. This one right here, we don't know exactly where that is. I think it's either Ontario or Michigan. This one is on Mars. And they are all very similar. They share all the same characteristics, and I don't think that there were glaciers on Mars. Drumlins themselves are an interesting characteristic. They have a direction of flow. They're supposed to have been made by debris being dropped by glaciers. If that's the case, this here is a picture of Mars. Again, this is 250 kilometers. These are the most massive drumlins you have ever seen in the history of ever. I would hazard to guess that they are not caused by any sort of glacier, especially on Mars, especially of that size. Note there's a part of bedrock. If I was to say what they seem to be in electrical terms, there are points where, that have been etched down, and they are stopping material from going around them, much like water would. That's why I can understand the confusion. But as you can see, they pay no heed to landscape, and they wouldn't do this, whatever this is. This looks like a feathering electrical effect that went across the landscape. But you can see that this was going across the landscape on top of this stuff that was already laid down. And here is a crater in the middle of it. So this is like a feathering discharge, perhaps moving, to give you an idea. It reaches for, and once it gets close to one of these points, this bedrock, it will jump to it. And as such, it leaves material around it. This is my interpretation of what I'm seeing. There's no air required. This is this cross-hatching we were talking about before. Here it is again. Right across here, right across here, right across here, right across here, and so on. Same with this, except it's going this way. And this cross-hatching is indicative of an electrical ionic wind, probably near supersonic if it's creating these cracks here, if not supersonic. And these drumlins are ionic debris laid down. This, if I'm not mistaken, is near Ontario, and that is on Mars. The trickiest one is, I noticed that there are tendencies where the charged sheath effect that we were referring to earlier, that you saw with the blue holes. Well, if you can see that as a sort of aurora ripping across the ground, not always in a tube form, then you can see what we might be seeing here when we talk about both. In the background is a picture of the Scablands, and this is Mars here. Now, you can see that there was a plateau, like this plateau here, like this plateau here, and part is being etched away. This is all being etched away during an excavation. However, instead of being built up far away like a prominence would take it, it's getting built up right beside itself. And this is what we're seeing here. This was sort of perhaps maybe a ionic wind, not unlike when you imagine the mountains that were Mount Everest and so forth, the Himalayas. They sort of have that curve to them out behind them. Well, this is similar to that, I would think, but it's very flat. So the ionosphere is coming close to the surface of Mars. There's no atmosphere really to stop this process. So it will work right beside itself without any cause for alarm. So it's etching here and depositing right here. And it built up this whole area as it went around this curve. It continued, probably because there was an overriding direction going this way. And as such, this just became a natural confluence. But this means that material can be ripped from a certain point and then deposited right beside itself. And as such, you're going to see material that might say it looks like something on top of something else, and something happened millions of years before that. How unlikely it happened in the same spot. It's not unlikely. It was the same event. And if you give an example of why we might not find so many fossils, is because you could have this happen where animals are killed and things instantly fossilized, lifted in the air, blasted to pieces and ripped apart, deposited as a fine debris field, and then they go, whew, at least we have this. Well, then just a few seconds later, lo and behold, here comes this other electrical phenomenon just etching the surface away, even on finer detail, and turns that what's ever left into fine, fine, fine dust. And that's it. Nothing of that creature remains that we would ever find. And this is the type of stuff that we're looking at here. This is why we see such violence in some of these things. And we also see the top layer infused by intense heat. As you can see across, some of these have melted tops on them. And you can see that in more than one place. For example, here's where you see, you might think this is a V-shaped trench, but as you can tell, if you look closely, it's not. Much, much longer slopes to these. and they are reaching up to a point. This plateau is where it was coming down from the sky, and this is where it was meeting. And anything above this point was removed upwards. Anything coming from the side would be brought in and deposited. And you have this buildup. Same thing here. Because you can see they get built up in this direction, heading towards this object. The equation, of course, the exact same as we discussed before. So you have Q on either side, you have a distance between the plates, you have the dielectric constant, and of course the area and the voltage. And this is exactly why they said the sky was falling. I mean, you could imagine what this would look like if it was able to change the landscape, or you were able to witness it without being dead. Those who did would be scarred forever. Now, with these effects, V-shaped trenching is no longer required. You can have things that are built up right beside themselves, usually with a definitive pattern between the two breaks. As you can see, this is building up to this point. Well, this is probably ripping off this material here. Actually, there's probably build up over here, but still ripping material off that was already laid down, building up to this point, and it's sticking to the top. This here, flat plateau, and then these towering columns. The hexagon shape, well, we've seen hexagons in craters. Why shouldn't we see hexagons in reverse in depositions? And in fact, we do. You can see how this would be formed, burning across an area, picking up, and then attaching to another area. Here's a perfect example. Material was being here, built up to this area. It lost its area. See, this is the surface area of the strike. It went down to this surface area up here. As such, it moved to this point, and material from here is then etched and built onto this area. And that's why it started under etching over here, and this part is still bubbling up and stuff and pulling material in. And this is why this is pitted and so forth. And you can see it also clearly here and so forth. So this is examples of material that would have been built up deep here, and then, okay, now it's going over here. It's only attached here now to these particular areas, ripping material out and putting it over here. And this is why we see some of these damaged or malformed canyons, because there is the positive and negative effect of the sheaths acting right beside one another. This is where you start getting into these weird melted terrains, very torturous, etching and deposition right beside itself. It's almost like it turns into a torrent. Obviously, this has to do with the magnetic fields. You can see the rippling, these columns. Here's a perfect example of rippling as it goes up them. Now, this could only happen if these were being built rapidly. You can see the harmonics, or the whatever it was resonating to, the vibrations of the earth, perhaps, that these things were being built up under. You can see that they were being pulled to one side. You can't pull these to one side if they were being built up geologically over millions of years or something. This is a instant or fairly instant process. You can see where they stop and start again. So here's random deposition. Or actually, this is probably the landscape as it was right here. And then this was being built on top of it. You can see where the heat has cooked it. And it's being built up in a very orderly fashion with these multiple hexagonal shapes. Think of those beards that we were referring to before, but in positive form. And then the order breaks down into chaos and begins building up. Now, of course, it can build up and over because it has a high metallic content. So it sticks to it even to the side. It doesn't require gravity to hold it there like it does if it's more silicate-based rock. This was the landscape before, right along this edge. So this is being ripped up here and deposited here. This basically would be the boundary layer. We see the same thing here. This is if I'm not mistaken, that's the Castle of Edinburgh. And you can see that this landscape is the exact same thing as described there. It is a landscape, then these hexagons are building up, and it goes back to chaos. And then a castle, apparently. Perhaps maybe it was built there for a reason. Perhaps it was holy. But let's move on. Tops will often have a melted terrain. Here is an example. Iron-bearing rock, basalt, highly conductive. So now you have an area which is going to be wanting to come right out of here. It won't pull out of here anymore. It will go to these high points. And this stuff protects rocks underneath. Not without getting damaged, of course. These are basically anodes that are getting worn down by constant electrical discharge. Here's a perfect example of it on top of a tuapi, I guess what they're called, in Venezuela. They are just tortured, melted terrain, etching down, reaching in, going, I can't get through this stuff. This stuff is protecting this rock, because this rock is really tasty. And see how I can get at it because it has high silica content or high calcium content. It will break off easily, and I can get at it. So it has to go in and then go under to get at that, because this rock is more conductive and it's protecting it from being etched away. And you'll see that with tent rocks and other places as well. This is basically how these, you see spheres that have landed and managed to protect the rocks underneath. That's why. They're basically giant lightning arresters. So you can see fused material on top of these things. This is just outside Albuquerque. And there is this layer. Me and Julie and Wes got to go here and look at these petroglyphs. But we noted that the rock was melted, but only on one side. It was like it was subjected to a flat layer of heat across the whole surface. So you can imagine this material here. You can see how it's broken up on the edges. This is what this edge here, or this edge here. This is what this is here. And this was like the material was overhanging, and then it would drop down. And as such, the material that dropped down was dropping down because underneath it was being etched away, and the mass of the rock was breaking off and falling down, or perhaps maybe it was being broken off and falling down. But either way, it was not getting lifted into the sky nearly as easily as the rock beneath it. Towers are where we get into the both category as well. This is Devil's Tower in Wyoming, obviously, and this is Monument Valley. They are both towers, and both are exact opposites with regards to what happened to them. This was a blob that got dropped and then built up from there. This used to be the landscape up here, and all of that was etched away, and this V shape was a perfect example of why that's occurring. You see this exact same thing on Mars. The reason I put them in the both category is because it's important to note that they can both create this effect, etching and deposition. Let's go look at a little bit more at Devil's Tower. There's a very large conglomerate base to it. A large blob of basalt landed on the ground. It had a different potential than the rest of the Earth, and as such, a lot of electrons were rushed to it. A lot of electrons could flow through it, and a lot of electrons did flow through it. The sky was looking for a place to land, so to speak. It found a place. This blob was super hot, very attractive, was not easily being removed from the land or anything like that. Material is being pulled in and deposited on it. You can see here, this isn't at the tower itself, but I wanted to use it as an example of what I mean by this forming all at once. These were semi-stable pieces of material that were standing, and they were standing while liquid hot, at least, or semi-liquid. Take a look here. These are bent over but not broken. They are made of basalt. They are hexagon in form. They're leaning over, not following the regular pattern. They probably got hit with a shock wave or something. Some of them seem to be fractured here. But this is clearly, this was a force pulling on this whole area up and out, and this was taken with it. And these were all in a state of Euclidity, at least, not unlike solder or lava or something. But they had to be semi-stable and independent forms themselves to do this. I hope that is self-evident just by looking at this picture, understanding what I'm talking about. Hopefully this will become even clearer when I go into further. Note, by the way, the top of Devil's Tower is burnt. It should be. The heat of being so close to the ionosphere, it was probably sticking right into it. The ionosphere dipping down so far that it's touching the top of the Devil's Tower. Here is a perfect example of it, the blob I was referring to from the side. And you can see it's pulled up. And it's so doing broken several times, probably from supersonic shock waves. Andy would probably give you a better example of that, but let me show you what I mean. Note, by the way, that these don't always happen. They still follow the same rules as before. So this whole area is building up. It no longer has enough current to do the whole area, so it starts doing a smaller area. And that's what we're seeing here, just what we saw before with other mesas. Except obviously these are hexagons. So how does that work? Well, you're going to have a lot of pillars of fire, each one of them little beards twisting, coming from the ionosphere, which is reaching down from up in the sky. These pillars are building up and building up and building up. As they hit a certain point, the ionosphere cannot let them go any higher. Anything above that certain point is lifted and is removed. However, this juncture, right up here at the top of this thing, must be loosely referred to as, because on the outside, as you can see just by looking at it, even though the inside is a bunch of little pillars, the outside is a giant pillar, because you have the same effect. Here it comes from the side, and it's going to be spinning around this thing. And that's what's happening here. It was probably blowing things off, things would go flying and so forth. But, be all end all, this would be giving off so much heat, it would be cooking the top of this thing, which is exactly what we see. To finish up, metamorphosis, sorting, geodes, concretions. I think now that you can begin to see how concretions and geodes, especially if we understand concretions as Z pinches that are rounded off pieces of material that fall back to Earth, not unlike planets. Geodes seem to be held within the Earth, not fallen back down, but held there. That's why they have a polarity to them. That is why they have a equatorial bulge, and that is why they have sorting electrically. They are basically Z pinches inside underground lightning bolts, if that makes sense. So we can see this cellular effect with those types of things. We can also see rippling and mangling of material. Most of this here, I know it sounds hard to imagine, but this might have been wriggling as if it was alive and forming layers as it was being reshaped by harmonics and everything else in the area. It is hard to envision what process of conventional geology created this. We can also see by the effects of electrical extraction, or what that means to exploration. If we could understand this a little bit clearer, we could begin to look in the proper spaces for things we've probably never seen before. This is just outside Los Angeles. These are columns that are right through the Earth. Now, the only reason we even noticed them is because of the weathering of water had come up here and worn them down. But they go right through the rock. They're not actual lightning bolts, but they are twisted. What they are plasma streamers reaching to the sky, looking for something to strike. Material is moved from the water through this rock up. Now, it didn't make a connection. Wherever the connection was, I don't know. But this didn't make a connection. But in the not making of the connection, the streamers themselves left their mark on the land. This is a cave in Mexico, just inside a volcano. These are gypsum crystals. There's no water that made that. This is 160 degrees inside, which is why you have to wear those protective suits that are air conditioned. And they're larger than houses. And crystals are drawn out of rocks as electricity is passing through it, which is why quartz occurs in veins with gold, for example. Just transmuted from the stone The gold is removed. Quartz is removed. We go looking for that because we think it's pretty. The Z-pinch remnants you can see all over the earth. The great stone balls of Costa Rica, for example. Here's some on the coast of, this is Antarctica. There's just these balls just sitting there. No, they're not made by man. No people from Antarctica made stone spheres. These were blasted open by people on Costa Rica. As you can see, they look like shells and iron-rich material separating different chunks that look like maybe they were squeezed together to form a sphere. Perhaps many of them hollow, as you can see. You can see these dikes going across the landscape. Garrett Hill did a wonderful presentation on this exact effect. These are very high-powered streamers traveling in the same direction, looking across the landscape, not unlike the rays of Tycho, not unlike eskers and drumlins. But they are welding material on top of themselves. They are like ley lines or dragon lines across the earth, except imagine how powerful they would be that the material right near them would be melting. And they're sending currents across the earth. That's what's happening. Probably because this mountain range was forming right over here. So current does have to travel, and it does have a resistance to go through, and it will tend to filament, and this is a perfect example of that. If there was charge over here, and suddenly there was a touchdown over here, the charge has to move from the ground, through the ground, to here. Well, the easiest way to do that is across the surface, and this is what it's doing. These are called lava bombs, but you can see clearly we have a polarity, we have a direction, we have striations on it. We have an equatorial bulge on it. I don't know what to say except for, we should be paying more attention. The polarity is hard to ignore. I mean, here's a tube of plasma. You can see an out, another out. This is just a current as it was traveling through rock, and it was turning everything into different materials as it did so. You can see here a polarity as well, positive, negative, crystal growing inside of it, sorted electrically. It doesn't end there, as you can see. Currents will, just like the Eye of the Sahara, attach down, but here it is a deposition. Material ringed, ripped up, but yet ordered. There's certainly more to it than we'd like to admit, or geology would like to admit. And it's our responsibility to begin to catalog, document, and to put these in some semblance of order. It doesn't matter immediately if the order is correct or perfect, but that we are able to recognize deposition from excavation, and to tell you when it is both, and to show you examples over and over again to prove, at least to a reasonable, open-minded individual, what is truly going on with the geology of the earth. Thank you very much.